Okay, so we are going to use our first derivative test. We know how to take the first derivative, but how can we use that to test for something more meaningful? As it says here, it's a test that we would use the first derivative. It's not the first test ever performed on a derivative. Okay, so basically we are going to use this test to determine if extrema are maximums or minimums. This will be very important for us. We know in math that we show our work to provide evidence for our conclusions. So lots of definitions here. These are going to get pretty wordy. Is pretty much common sense. Okay. The function f is increasing on an interval if for any two numbers x1 and x2 in the interval, so some x value 1, some x value 2, that x1 is less than x2 implies that f of x1 is less than f of x2. Let's just show that visually because there's going to be lots of questions, and before we move on to decreasing, it's important for us to understand. So this is x1 and x2, right? Clearly x1 is less than x2. So f of x1 is less than f of x2 would imply that it's increasing. Okay, so that's what this wording is describing, and it'll be the same pretty much for the rest. F is decreasing if for any two numbers x1 and x2 in the interval x1 is less than x2. It implies that f of x1 is actually greater than f of x2, so reverse. And then it's content. That doesn't even make sense. It's constant if for any two numbers x1 and x2 in the interval x1 is less than x2 implies that they're equal. Their y values are equal. Again, we know this. Also, I just want to point out that this notation here, x1 less than x2, is just talking about as we move on the graph from left to right. Okay, so a theorem. Yay! Given that f is a function that is continuous on the closed interval a to b, and it's differentiable on the open interval a to b. Now this is starting to sound repetitive. We had the same conditions for Rolle's and mean value theorem. Okay, anyway, same conditions. Then, if f prime of x is greater than 0 for all x in the open interval, then f is increasing on a to b. If f prime of x is less than 0 for all x in a to b, then f of x is decreasing on a to b. And last but not least, if f prime of x is equal to 0 for all x in a to b, then f is constant on a to b. Okay. What's this talking about? Okay, so these are the intervals that these things are true. Now remember, we know that derivative is the same thing as slope, right? So it's saying if the slope is positive from a to b, clearly it must be increasing. If the slope is negative from a to b, the slope on f is decreasing. Let's point out that we're talking about f. And then if the slope is 0, then it would be constant, okay? These are things that we kind of already know. I also want to point out that we're talking about the slope on this open interval. And if you're wondering why it's the open interval and not the closed, well, we wouldn't say that it's differentiable at the endpoints. Okay? Okay. Next definition, strictly monotonic. Now that sounds cool. You better throw that in your casual conversation with your friends at lunch and you'll sound super smart and people are like, wow, you're smart. I want to be you. They do say smart is pretty. Anyway, a function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. So, for example, like we know f of x equals x is strictly monotonic because that's increasing on its interval. We also know like x cubed is strictly monotonic. We could also say, you could even have, a negative slope, negative x or negative x cubed. I'm just coming up with random examples. Obviously, there are so many more. Okay, so one thing that I want to point out, because it's easy to understand what strictly monotonic is, but let's understand what not monotonic means. So let's say, for example, I have this graph. That's supposed to be constant, sorry. You know, from here to here, it's constant. F prime of x is 0. Okay, so even though this is increasing and this is increasing, even though here it's not negative, but it is 0, so that's not considered to be monotonic. All right, more theorems. Okay, so here's where we get to the first derivative test. Yay! Okay, we can do this. Given that f is continuous on an open interval I containing c, c is a critical number of f on I. What does it mean to be a critical number again? Oh yeah, that means that the derivative is either 0 or undefined at that point. Okay, and f is differentiable on I, except possibly at c. Then, if these three conditions are met, if f prime of x is less than x for on the interval to the left of c, and f prime of x is greater than 0 to the right of c, then f of c is a relative minimum. I'll explain this, don't worry. If f prime of x is greater than 0 on the interval to the left of c, and f prime of x is less than 0 to the right of c, then f of c is a relative max. And if it does not change sign, the derivative does not change sign, then it's neither a max or a min. What? Okay. First, deep breath, relax. It's okay. We actually already know this. So let's say I'm gonna do this. Let's make this C. So we're taking a look at the first one. Here, f prime of x would be negative. Here, f prime of x would be positive, right? The interval to the left, the interval to the right. If these are true, then we would say that f of c is a relative min. Oh yeah, that makes sense. Just to take a look at the third one, I think you guys can figure out the second one. If it doesn't change sign, so let's say it's like this guy, so let's say this is c. So this was, let's say, positive slope, didn't change sign, so this is neither a max or a min. Huh, makes sense. Good thing we didn't freak out, right? All right, so relative extrema. So let's take a look at this visually. Let me draw a graph. You should draw the same graph. Okay. We're going to have our interval. Let's put an A here, B here. I'm just going to make this a -1. Make this a 4. Again, we're just making something up to help us understand this a little bit better. I'm going to make that an open circle because we want an open interval. And okay, that's in line with 4, if you can't tell. I know it's not technically, but just use your imagination. Okay, so let's take a look here. First, what are our critical numbers? This is our graph of f of x. Remember, critical numbers are where the derivative would be 0 or undefined. So the derivative would be 0 at, great, a and b. Here and here, those are our critical numbers. Okay, now let's point out the fact that this is a relative max. This is a relative min. Let's also point out that this is nothing. Why? Well, I mean, it's an open interval, right? And this is nothing. So we might be tempted to say that these are absolute maxes and mins, but they're not because they're open. And let's also point out where they're increasing or decreasing. That's going to be really important for us. And it's something that you'll be required to do. So it's increasing from -1 to a. Anywhere else? Wonderful. And b to 4. And it's decreasing from where do you see? Excellent. Good job. A to b. Great. So This is just understanding maxes or mins relative to the open interval around it. Relative extrema. Let's take a look at absolute extrema. Not the Ohio State, the highest and lowest point on the function on a given interval. So please allow me to draw a graph. Let's I learned my lesson. It's better to draw the graph and then mark the axis. Okay. So here's my new graph. Okay. Once again, let's identify our critical numbers. Critical numbers. Where the derivative would be 0 or undefined. It would be 0 at A. Wonderful. We could also point out that at A, what would we call that? We would call that a relative and an absolute min. Why is it absolute? I mean, it's the absolute lowest point on the graph. Why wasn't this an absolute min? Well, look, there are a bunch of these points that are lower than it, so that wouldn't work. Once again, just to be mean, this says nothing, and you're nothing over here. Okay? If you're wondering why this isn't a relative max, because, it's closed this time, but if you look, there are points that are above it. Right? It's not relative because it's an endpoint, but also it's not absolute because these points above it. All right, last but not least, increasing. It's increasing from A to 3, and it's decreasing from 1 to A. Awesome. Okay, so we are going to try this example first together, and then, of course, I will have you try some on your own. Wonderful. All right, we got our polynomial here. What's the domain of all polynomials? You guys are so smart. Infinity to infinity. Wonderful. Let's find its first derivative. I know you're like, man, I miss doing derivatives. So if you miss it so much, then you should just try some on your own for fun. All right, let's find our critical numbers. So remember, we set our derivative equal to 0. We get 0 equals 6x times x minus 1. So we get some critical numbers of 0 and 1. Coolio. My sister makes fun of me when I say coolio, but I still do it. Okay, next we're going to determine where the graph is increasing, decreasing. Now, obviously, this is much easier when we have the actual graph, but we don't. So what we're going to make is what's called an increasing, decreasing chart. Follow along and make sure you are doing this consistently in your problem sets. Now, we're going to make an increasing, decreasing chart. We're going to use our first derivative, so I'm going to label this chart as f prime. Okay. I'm going to plot my critical numbers. These are where my derivative was 0. That was 0 and 1. And I'm going to test out if it was increasing or decreasing in between these intervals. So for example, let's say I wanted to test out -1. Use easy numbers. I'm going to test out 1/2 here, and I'm going to test out 2 here. Okay, so I'm plugging this into the derivative. That's why I label this line, so that way you know what I'm plugging into. I'm going to plug in -1 into the derivative. And what do we get? Is it positive or a negative number? It's a positive number. If I plug in 1/2 into the derivative, we would get a negative number. And if I plug in 2, we would get a positive number. What that number is doesn't really matter. It just matters about its sign. Okay. So again, this is called an increasing, decreasing chart. So now I can actually answer this. Now I say, okay, well, it's increasing. Remember, increasing is where the slope is positive. From -infinity to 0 and 1 to infinity. And it's decreasing from 0 to 1. Okay, wonderful. Now we have to decide, do we have a maximum or a minimum? Now, Remember, these are our critical values, and relative maxes or mins can only occur at locations of our critical values.